Today we're going to be talking about how to find the distance between two planes, and in particular, the distance between two planes that are parallel to one another. In this particular problem, we've been given the equations of two planes. One is 2x minus 3y plus z equals 4. The equation of our second plane is 4x minus 6y plus 2z is equal to 3. We're going to be using the distance formula here, which we've defined for d, where d is the distance. D equals this value here, and we're going to get a little bit more into that in a second. But the first thing I want to show you how to do is just to verify that the two planes are parallel. The way that we do that is by finding the normal vector for each plane and then comparing the ratios of their component values. So here's why that works. The normal vectors to each of these planes, remember that a normal vector is perpendicular to a plane. If we're talking about these planes being parallel, their normal vectors will also be parallel. If you think about, or if you can picture here, two planes, let's pretend we're looking at them end on, right? And so we have a plane here, we're looking at the end of it. We have another plane here. These are parallel to one another. Their normal vectors are perpendicular to the plane. So this is the normal vector of our first plane. This is the normal vector of our second plane. And you can see that these normal vectors are also parallel. So one way to verify that your planes are in fact parallel is to compare the normal vectors to see whether they're parallel. And here's how we do that. We take the coefficients on our x, y, and z terms on the left-hand side here. So x, y, and z, like this. The normal vector of this first plane here are these coefficients 2, -3, and 1. Make sure that if you have a negative sign that you include it. We have this minus 3y, so we have to say -3. The normal vector for our second plane will be the coefficients here 4, -6, and +2. So these are the two normal vectors to our planes. The way that we verify that these vectors are parallel is by taking the ratios of their component values, and here's what we mean by that. The x components in these vectors are 2 and 4, so we have 2 divided by 4 when we take the ratio of those values. We're going to set that equal to the ratio of our y components, so -3 divided by -6, and then set that equal to the ratio of our z components, 1 divided by 2. As you can see here, if we simplify, 2 over 4 becomes 1 over 2. -3 over 6, our negative signs will cancel, and we're just left with here positive 1 over 2. You can see that we have 1/2 equals 1/2 equals 1/2. When this equation is true and the ratios are all equal to each other, we know that these two vectors are parallel. And because we know that these two vectors are parallel, that also proves that the two planes are parallel. So that's how we verify that our planes are in fact parallel to one another. Now when it comes to finding the distance between them, here's what we want to do. We actually want to reduce this problem instead of a distance between parallel planes problem. We want to reduce it to a distance between a point and a plane because that's easier to deal with, and that's what this formula here for distance describes, the distance between a point and a plane. Well, how are we going to do that? All we need to do is find a point on one of our planes and then calculate the distance between that point and the other plane, and we'll have it. So how do we find a point on one of our planes? Well, let's take our first equation. Let's find a coordinate point on this plane here. The way that we're going to do it is by setting y and z both equal to 0. When we do that, our y and z terms are going to go away here, and we're just going to be left with 2x is equal to 4. So you see how we did that? The -3y and the z drop away because we set y and z equal to 0. That leaves us with 2x is equal to 4, and then we divide both sides by 2 and we get x equals 2. So we have an x value of 2. We got to x equals 2 by setting y and z equal to 0. So our coordinate point, one coordinate point that lies in this plane, is the point 2, 0, 0. Now all we need to do is find the distance between this point and this plane. Here's how we do that. Our distance formula, and I go into a little bit more depth about this distance formula in another video I have about the distance between a point and a plane, which is what we've reduced this problem to essentially. But we're just going to pull the values in this formula out of these two point and plane equations here. So from our equation of the plane, we're going to pull out the following values. The coefficient on our x term, 4 is going to be our value of a. The coefficient on our y term, in this case -6, will be our value for b, and the coefficient on our z term will be our value for c. When we have our constant over here on the left-hand side, this value here of 3, that's going to be equal to -d. Sometimes the equation of the plane will be written this way. You'll have 4x minus 6y plus 2z minus 3 is equal to 0. So sometimes that constant is over here on the left with this whole thing equal to 0 on the right-hand side. When that happens, you take this -3 value and say that that's equal to positive d. So however your equation is arranged, you can find a value for d. In this case, when the constant is on the left-hand side, you say that this value, including the sign, is equal to d. If your constant is on the right-hand side, you have to multiply this value by -1 to get -d. So to plug in for positive d into our formula, we're going to be plugging in a value of -3. d is equal to -3 here. The only other values in our formula are x sub 1, y sub 1, and z sub 1, and those are going to come directly from our coordinate point here, x sub 1, y sub 1, and z sub 1, like this. So now in order to find distance, all we have to do is plug into our formula. So we're going to have d is equal to the absolute value. These are absolute value bars. They don't indicate the magnitude of this value in the numerator. So we're going to have the absolute value of a, which we know is 4, times x sub 1, which comes from our coordinate point here, that's 2, plus b, which here is -6, so -6 times the y value from our coordinate point, which is 0. Then we add to that c, which is 2 right here, so 2 times the z value from our coordinate point, which is 0. And then remember for d, we're plugging in -3 right here. So we just say for d, -3 or -3. And then in our denominator, we're going to have the square root of a squared. A is 4, so a squared is 16, plus b squared. B is -6, so b squared is positive 36, plus c squared. C is 2, so c squared is 4, and we're going to be taking the square root of that sum. D, therefore, is going to be equal to 8. This is going to go away as 0. This is going to go away as 0, so just 8 minus 3 in our numerator. In our denominator, 16 plus 4 is 20, plus 36 is 56, so we'll do the square root of 56. In our numerator, 8 minus 3 is 5. The absolute value of 5 is still just 5, so we get d is equal to 5 divided by root 56. Now remember, we can simplify this fraction here because we can simplify root 56. We'll get d is equal to 5 divided by, remember that 56 is the same as 4 times 14. We can pull out a 4 because we know that the square root of 4 is 2. I know we can pull out a positive or a -2, but because we're dealing here with real distances, we want to take the positive value, or just positive 2. So we'll get 5 divided by 2 times root 14 as our final answer for distance, and that's how you find the distance between two parallel planes.